In this video, we're going to have a look at the compound angle identities, also known as the angle sum and angle difference formulae in trigonometry. Now, these have already been established in your Year 11's methods course. So what we're going to have a look at is particular questions where we're asked to simplify, solve for all values of an angle, and also prove some identities using these compound angle formulae as assisting us to do so. So I listed them here for you so that we can make reference to them as we go through these questions. In our first one, we're asked to simplify. We've got cos 7x times cos x plus sine 7x times sine x. So I can see that directly relates to the identity involving cosine. And I can see that I've got a plus. So I know that it's going to be the cos of 7x subtract x, which I could write as cos of 6x. In our second example, we've got sec of x minus pi. I'm going to rewrite this as 1 over cos of x minus pi. So now I can take the denominator that we've got involved here and expand on this. So this is going to be 1 over cos of x times the cos of pi plus sine of x times the sine of pi. Now, evaluating this a little bit further, we can't change the cos of x, but we know that the cos of pi, which is 180 degrees, is worth -1. So that's going to be negative lots of cos x. And I've got plus the sine of x times the sine of pi, or the sine of 180, which is 0. So that's going to eliminate that term. So what we end up with is the negative of 1 over cos x, which is equal to negative sec x. Now, if we stop and consider the graph of the secant function and where the asymptotes lie, and the parts of the graph that form one period, if we shifted this graph right by pi or 180 degrees, in fact, we're talking about that second section of the graph where we have that curve below. So that's where that 180 degrees is going to fall. And so that's going to makes a lot of sense that we're going to end up with the negative of the secant of x. Let's consider our second question here, determining the exact value of sine 15. Now, going back to looking at our compound angle identity involving sine, what it tells us is, sine A plus an angle B, or the sine of an angle A take angle B. Because we want an exact value, we have to involve either something like 90, 60, 30, or 45. So I'm going to use 45 subtract 30 to represent the sine of 15. So if I expand on this, this is sine 45 times the cos of 30 take the cos 45 times the sine of 30. And evaluating these exact values, I've got root 2 on 2 times root 3 on 2, subtract cos 45 is root 2 on 2 times a half. Multiplying these fractions together, I've got root 6 over 4, subtract root 2 over 4, in which I can combine to root 6 take root 2 all over 4 as an exact value. So let's have a look at a solving question. We want to solve sine theta equals cos theta minus pi on 6 for all values of theta. As you can see, we're dealing with radians here. So I'm going to focus on that right side here just to expand on this. So I've got cos theta times the cos of pi on 6. And because I've got to subtract, it's going to be plus sine theta times the sine of pi on 6. And evaluating this, we've got sine theta equals, I know cos pi on 6 is cos 30 degrees, so that's root 3 on 2 times cos theta, plus sine of 30 is a half, so I've got half lots of sine theta. what I can recognise is I've got 1 whole sine theta plus a half on the other side. So I'm going to subtract that half sine theta. So I've got a half sine theta equals root 3 on 2 cos theta. Now we could multiply through by 2 and that will get rid of these denominators. And I'm also going to divide by cos theta on both sides. So I've got sine theta over cos theta on the left, and dividing by cos theta on the right is going to leave me with root 3. And nicely, this ends up being tan theta equals root 3. Now thinking about tan of an angle being root 3, I know that's going to be pi on 3, so that's my reference angle here. So theta is going to equal pi on 3. Thinking about that unit circle, just with 0 to 2 pi, for example, I'm going to have pi on 3 and it exactly pi degrees separating its next solution. So that's going to be pi on 3 plus pi n, where n is an integer. So a slightly different question, which I'm sure you've seen the setup of before. And I'd like you to pause the video and have a go at this question. But first we'll read through it. If A is an acute angle, where the sine of the angle is 7 over 25, and B is an acute angle where cos of B is 3/5, determine the value of sine A take B. So think about setting up, because you've got 2 trig ratios that you're given, think about setting up some triangles to represent those, and pause the video and see if you can evaluate sine A take B. So taking a look at this question, we can set up those right triangles to show that sine A being opposite over hypotenuse is 7 on 25, which would make this unknown sine 24, and the cos of B being 3/5, that unknown opposite side will be 4. Now Pythagorean triples. So setting up sine A take B, we can work out we have a solution of negative 3/5. So now let's think about proving some statements or equations using these compound angle identities. So again, when we're doing a proof, we either want to concentrate on the left-hand side or the right-hand side and then prove that it's equivalent to the alternate. So I'm going to start here with cos 360 plus theta equaling cos theta. I'm going to start with the left-hand side. So I'm going to expand on this one. So this is going to be cos 360 times cos theta. Subtract sine 360 sine theta. So I know that the cos of 360 is equal to 1. So I've got 1 lots of cos theta. And the sine of 360 we know is 0, lots of sine theta. So that term is going to disappear, and we end up with cos theta, which equals the right-hand side. So now it's time to pause the video again and have a go at proving the next equation. So I've taken the left-hand side in this situation, and I've just expanded on the sine of A plus B and then subtracted the sine of A take B. Just careful to use our brackets because we have a subtraction which is going to affect that subtract inside the bracket. You can see that some terms cancel out, and we ended up with 2 cos A times sine B, which equals our right-hand side. So let's have a look at a proof involving tan. So we've got tan of theta plus pi on 4 equals 1 plus tan theta over 1 minus tan theta. So I'm going to take the left-hand side and use the compound angle formula for tan. So this is the tan of theta plus the tan of pi on 4, all divided by 1 minus, it's a funny looking one, tan theta times the tan of pi on 4. So just evaluating tan of pi on 4 or 45 degrees, we've got tan theta plus 1 over 1 minus 1 lot of tan theta. So I can see straight away that I've equated the bottom part of the fraction on my right-hand side straight away, and I've actually simplified to equaling the top. I've just got it in a different order, but that's not going to make a difference here because both our terms are positive, so we can say this equals the right-hand side. So in our last proof question here, we've got cos x plus y times cos x minus y equals cos squared x take sine squared y. So I'm going to start with the left-hand side, and I'm going to start this off for you. So I'm going to expound on both of those. So we've got quite a large expansion to do here. We've got cos x times cos y, subtract sine x times sine y, multiplied by, so I'm going to put that in brackets. We've got cos x times cos y plus sine x times sine y. So expanding this, we can see that we've got a binomial expansion here, so we're just going to be careful with our squares. So we've got cos squared x times cos squared y. We've got cos x cos y times sine x sine y. And then we've got the subtraction of exactly the same thing. So I'm just going to cross that out because when I expand that, the middle terms there, that would subtract it. And then I've got to take sine squared x times sine squared y. So just having a look at what we're dealing with here, I'll write these next to each other. We're getting very close to that right-hand side. So essentially we're wanting to keep this sine squared y and cos squared x in both of those terms. So what I'd like you to do now is pause the video and think about how we're going to manipulate that cos squared y and that sine squared y in order for those two not be included to equate as our right-hand side. So think back to the other compound angle identities or even the Pythagorean identities where cos squared y or sine squared x may be involved. So we're going to use the Pythagorean identity here. That's cos squared x plus sine squared x equals 1. So let's just focus on this first cos squared y. So we're going to rearrange the Pythagorean identity to say 1 minus sine squared y instead of the cos squared y. So we've got cos squared x times by 1 minus sine squared y. And let's do the same for the sine squared x. Let's make that 1 minus cos squared x times the sine squared of y. I'm just going to put that in another bracket so we can clearly see that's subtracted. So we end up with cos squared x take cos squared x times sine squared y. Expanding, take sine squared y plus cos squared x sine squared y. And as we can see, we've got two terms that are going to cancel each other out. That's going to leave us with cos squared x times subtract sine squared y, which in fact equals our right-hand side.